Hi, I'm Josh Mehling, NASA's Principal Technologist for Robotics.
And I'm Danette Allen, the Deputy Lead for NASA's Autonomous Systems Capability Leadership Team and the Senior Technologist for Intelligent Flight Systems.
As NASA looks to the future of exploration, returning to the moon and going on to Mars, establishing a sustainable presence at these destinations, and tackling an array of science objectives across the solar system, it's clear that we need continued technology advancement to accomplish our mission and meet our future needs.
But NASA can't accomplish this alone. Engaging partners across industry, academia, other government agencies, and the international community is a key component of our strategic framework, and we welcome any and all feedback on our strategic vision, the envisioned future states we're targeting, and the technology priorities that will get us there. The purpose of this presentation is to take a look at the autonomous systems and robotics domain, to share with you our current thinking, and start a conversation on how we go forward together to enable the exciting science and exploration ahead of us.
So what is NASA's interest in autonomous systems and robotics? The key word, I think, is that it is enabling. Autonomous systems and robotics is a broad, multidisciplinary domain with a diverse set of component technologies. And advances here and the integration of these advances into new, more capable systems will enable high priority outcomes across NASA's science and exploration portfolio, be it establishing lunar surface infrastructure, planetary science investigations, in-space servicing, assembly and manufacturing, or any number of other mission activities. And the attached chart package outlines a development strategy geared toward advancing autonomy and robotics to provide the necessary foundation to enable these key objectives.
Autonomous robotic systems are critical to meeting the challenges of NASA's new missions. Missions that travel farther, operate longer, and behave reliably in extreme and dynamic environments. To gain the performance we need at the pace we need to increase space mission effectiveness, productivity, and safety will require the entire autonomous systems and robotics, or ASNR, community of practice. Academia, industry, and government working collaboratively to respond to the needs of commercial missions, human exploration missions, and science missions. To reduce barriers to collaboration, NASA aims to adopt an open framework to enable the distributed development and integration of modular, interoperable, and reusable capabilities. These capabilities will form the ASNR foundation across 6 different envisioned future technology objectives. While ASNR are tightly entwined in this domain, the first 3 objectives focus more on the autonomous system behaviors than on the robots themselves. First, multi-agent systems for science and exploration offer several advantages. Distributed, homogeneous, and heterogeneous agents can work independently or interdependently towards a common goal to achieve a mission, even in the face of attrition or single-agent failure. As the agents are distributed, so are the risks. The example shown here is an autonomous constellation of spacecraft taking science measurements, ideally driven by both the data and its real-time trends, as well as human teammates that are part of the autonomous science mission. Second, adaptive and fail-active or fail-safe autonomy is an objective for all of NASA's autonomous missions, but is especially important in the high-risk, dynamic, and uncertain environments of interest to our science community, who may have only one opportunity to observe an isolated event. Third, as we seek to build infrastructure on the moon and a lunar economy on our way to Mars, we require efficient and productive on-board autonomy for persistent and reliable worksite operations, including crew health and safety, as well as, not unlike the previous objective, high progress rate science collection platforms such as rovers and other unmanned robotic systems.
Continuing to target autonomous robots that support, augment, and enable the agency's science and human exploration goals. Our 4th technology objective is remotely operated intravehicular robotics for maintenance and utilization. This specifically envisions robotic systems capable of tending spacecraft or habitats in the absence of crew. But it also has a natural extension to the robotic mobile manipulation required to assemble and outfit equipment on the lunar surface, or continue to perform science objectives in situ, even when our astronauts aren't present. Of course, many of the future missions that NASA is envisioning will require robust robotic mobility capable of accessing extreme terrain or challenging locations as we push toward reaching hidden resources in permanently shadowed craters or making new scientific discoveries. So we have a key objective to develop the robots that enable these challenging explorations. And our sixth technology objective is all about going back to the moon and onto Mars in a sustainable way, with durable, self-maintainable robots capable of surviving long-duration operations while doing the heavy-duty excavation and construction work required to establish infrastructure in advance of crew and in support of a long-term presence on the surface. Autonomy and robotics capable of getting where we need to go and then doing real, useful physical work for extended periods of time in dynamic conditions to support our mission objectives once we're there.
No single entity has a monopoly on the state-of-the-art in autonomous systems and robotics. Cutting-edge spacecraft autonomy technologies are found across the community, including academia, industry, and government, as you can see in the example shown here. Missions, such as NASA's Distributed Spacecraft Autonomy, or DSA, are developing capabilities that push the multi-agent mission envelope. Honeybee Robotics' stochastic fail-active task planning approach for Europa is an example of a capability that is needed for self-adaptive autonomy in general. And Carnegie Mellon University was a pathfinder in 2015 when its autonomous rover traversed 26 kilometers in 10 days across the Chilean desert, an analog for Mars.
Again, there has been and continues to be great work done across all of our areas of interest. So we certainly don't mean to suggest that we can capture a comprehensive list of state-of-the-art development in just a few charts. But the examples listed do provide a few useful markers to gauge what we've done to date and identify areas of potential future investment, be it dexterous manipulation on the International Space Station or regolith excavation for the lunar surface. Your feedback is critical to this assessment, though. So please help us understand the technology gaps that exist from your perspective, the important prior work that should be leveraged or extended, and the right strategy as you see it to integrate these pieces together to realize our envisioned future. And this future doesn't just belong to the Space Technology Mission Directorate, or even only to NASA. There is a demand for autonomous systems and robotics coming out of the current Artemis architecture and NASA's Moon to Mars objectives. But we also see this pull from the broader science community and the growing commercial space industry as the need for and benefits of greater autonomy and more capable robots continues to grow. Part of NASA's role is to encourage that growth and ensure our technology development targets the autonomy and robotics needed to support the broad community working together in exploration, science, and the space economy.
Of course, NASA is already pursuing autonomy-enabling and autonomy-related projects. On the left is a list of around 20 ongoing efforts at different levels in the TRL spectrum across a wide range of funding models. The Space Technology Research Grant Program, or STRG, maintains a low TRL technology portfolio from academia. The Small Business Innovation Research and Small Business Technology Transfer Programs, or SBIR, STTR, provide funding to small businesses to encourage and enable the commercialization of innovative technologies that fulfill NASA needs. NASA's Game-Changing Development Projects, or GCD, advance space technologies via internal R&D teams that transition new ideas through analytical modeling, ground-based testing, and spaceflight demonstration of payloads and experiments. Growing the space economy and workforce in autonomous systems and robotics will take teamwork. For example, it will take teamwork across NASA mission directorates. As we develop new space technologies, we should seek to leverage investment from aeronautics, science, and exploration systems, with testbeds being a prime area for early adoption. These types of testbeds are part of the research development, test, and evaluation pipeline that enables NASA to develop prototypes, to bring down the tall poles, and reduce risk for transition to industry. We also need teamwork across academia, industry, and government. We must collaborate to integrate technologies for flight missions as ASNR technologies are drawn from industry and NASA. This will require an open framework to create sustainable, industry-driven hardware and software that's modular, reusable, and interoperable. Not only will this integration require an open framework for hardware and software, but we will also need accompanying standards, benchmarks, testbeds, tools, etc., that are available to the entire ASNR community. A public catalog would help to motivate continuous tech transfer and reuse across the entire community. A specific example that is in work now is Space ROS. ROS, first 1 and now 2, has emerged as the de facto standard in the academic and industrial ASNR communities, and its adoption has led to rapid advancement of capabilities and a broader, more accessible developer community. Space ROS is a version of ROS 2 that will meet verification and validation requirements that aerospace software must meet before being used in a mission.
And this is the same story across the board. If we look at human spacecraft support, for example, there are unique technology needs to provide versatile, autonomous mobile manipulation for remote robotic intravehicular maintenance and utilization. Some of these technologies are being pursued for terrestrial applications, and we'd like to leverage that overlap, while some need targeted development unique to the space environment. And leveraging an open framework approach allows infusion from NASA, industry, academia, and the international community to enable cooperation and interoperability across different vendor systems. It also makes extending these technologies to new use cases much easier, as you can imagine the similarity between a robot manipulating science equipment on board Gateway and a robot manipulating power connectors on the lunar surface, particularly in the underlying autonomy. We don't want to reinvent the wheel, and we think that mentality has a lot of value as in-space commercial activity and the stakeholder community continues to grow. The last few charts in our autonomous systems and robotics package highlight a number of important technology gaps that need to be addressed to realize our envisioned future. And again, our strategy is composed of two components: an approach to development built around the concept of an open framework, and the technology gaps themselves that need focused development to advance our current autonomy and robotic capabilities. We encourage you to review our package in detail and provide your thoughts on our target technology objectives, the relevant gaps we have or haven't identified to meet these objectives, and how best to foster a community of developers to realize the technology maturation and the versatile array of autonomous and robotic systems we need to enable the future of in-space exploration, commercial activity, and scientific discovery.
On behalf of NASA STMD and for Autonomous Systems and Robotics, Terry Fong, Josh Mehling, and myself, Danette Allen, we look forward to implementing this strategy for interoperability and tech transfer as we build a space economy together. We are eager to build the ASNR community with TIMS and outreach to industry through direct relationships with many of you and with the help of the Lunar Surface Innovation Consortium, or LSIC, as we make progress towards the ASNR envisioned future. Thank you.